Hello and welcome to this seventh and final atomic session. And just looking back over the past few sessions, we've been trying in a fairly simple way to kind of model what's going on in the atom with electrons and had a certain amount of success with the Slater's rules. Then we went on to the modified Slater's rules and we had more success with those, particularly with the transition metals. We found they predicted 4s being occupied before 3d. We found they predicted 4s electrons being ionized before 3d. We also found that it predicted chromium having the 4s1 3d5 configuration, so we had some success with those, but it didn't work all the time in that first series of transition metals. And so just to remind you, here are the anomalies that we have to take into account. The fact that chromium and copper had just one 4s electron to get either a half full or a completely full 3d subshell. And so we did come up with an explanation to do with this, talking about half full and totally full subshell stability, which you can rationalize in terms of pairs of parallel electrons. So we looked at this at the end of last time. And just when we thought everything was beginning to make sense, we look at the second row and we get a bit of a nasty shock, because the configurations in the second row neither match the basic rules we were following, nor the exceptions that we came across in the first row. It's beginning to look a bit random here. So you see niobium there, there's just really no logical argument based on what we've done so far about why that should be 5s1 4d4. Likewise ruthenium, I mean, what's going on with 5s1 4d7? Rhodium, again, no obvious reason for 5s1 4d8. And palladium, even weirder, that's 5s0 this time. That's bizarre. I suppose you get a 4d10 out of it, but again 5s0 is rather unexpected. So just as we're recovering from that shock, we might go and look at the third row and it gets even worse, because it's not even consistent with the second row or with the first row. So you see there with tungsten, 6s2 5d4, well, I suppose you could argue that is predicted by the Aufbau principle, but remember this is underneath chromium, so the half full shell hasn't come into effect, giving us 6s1 5d5. Then platinum there, 6s1 5d9. Well, I mean, that doesn't fit any kind of trend, and in fact if you look down the nickel palladium platinum group, all three of them, they're all inconsistent. They go from 2s electrons to 0s electrons to 1s electron in the valence shell. So we're really struggling now to try and make sense of this. So a bit of a setback looking at the second and third row of the D block. But then actually there is something I came across that looks like a kind of a magic bullet. And what is this thing? Well, this thing is called Rich and Suter diagrams, which I thought would be quite interesting to look at today. And so what they did in their approach, bearing in mind this earlier idea we came across that you get special interaction between parallel pairs of electrons, spin parallel pairs of electrons, Rich and Suter decided that they would split the subshells in two, just considering either spin up or spin down electrons. So in this diagram, we've got two energy levels for 4s, called 4s alpha and 4s beta. So you can consider alpha to be spin up and beta to be spin down. And likewise, the 3D subshell is split into two levels, alpha and beta. And so actually using this diagram, we can follow a kind of Aufbau approach where we stick the electrons in and see what electron configurations are predicted. So scandium, for example, there on the left-hand side, first of the D block elements. So scandium, you've got 3 electrons in there outside the argon noble gas configuration, and so we'd fill them up from the bottom. So the first electron goes into 4s alpha, and because obviously an s orbital can only take one spin up electron, so then the second electron goes up to 4s beta, where it has to be a spin down electron, and then the third electron to go in would go into the 3d alpha, so it'd be spinning up there in the 3d subshell. Of course, this is exactly what we see normally in the scandium electron configuration. Then we can go on to titanium and vanadium. So again, it's a similar kind of pattern. We're gradually filling up the 3D subshell there. And so I was going to give you a little exercise here, where for the other elements, you can test using this kind of Aufbau arrangement, gradually putting the electrons in, see which electron configurations are predicted by these Rich and Suter diagrams, and compare them to what we know to be the electron configurations. So I'll give you a little minute to do that. You can pause the video, then I'll come back in a sec with the answers. So here we are. These are the answers, and so you can see what I've done here is on these lines there, I've written the number of electrons in each of these kind of half subshells. And so you can see there the 3D alpha that has a maximum occupation of 5. Obviously you can only get 5 spin-up electrons in a 3D subshell, likewise 5 for the beta 3D subshell. And so there you go, we've just applied these ideas going from left to right across the period. And actually when you add up the 2 sets of d electrons and the 2 sets of s electrons to get your electron configuration, you find they completely conform to the observed electron configurations. So for example, looking at element 24 there, that's chromium, you've got your 4s1 3d5 dropping out of this, and likewise when you go to copper there, element number 29, looking up there you can see you've got your 4s1 3d10. So even those 2 exceptional atoms, they come out with the observed configuration. So I mean, it looks remarkably successful. It's got the correct one in every case. Now we can go on to the second row of the D block. Similar sort of thing, except this time we've got the 5s and the 4d having gone down a row in the periodic table. So we can do exactly the same thing. We can, knowing that each half of the 5s subshell is going to take 1 electron each half of the 4d again is going to take 5 electrons each. We can fill them up Aufbau style and see what we get. So there you go. I'll give you a little moment to work through this, and I'll come back give you the answers in just a second. So onto the second row D block answers there. So similar sort of thing. We've just followed the rules with 5 and 1 electrons in half of the D and S subshells respectively, and again we get the observed electron configuration every time. So far so good. So it's 20 out of 20 so far with the first 2 rows of the D block. And now onto the third row of the D block. So down to 6s and 5d subshells now. So yep, hopefully you're getting used to this now. Have another go putting the electrons in and see what you get. And here we've got the answers for the third row D block configurations, just following the rules that we saw before, and amazingly they're all correct again. So all 3 rows of the D block there, atomic configurations 30 out of 30, all of them predicted correctly. And in fact, amazingly, the success of the Rich and Suter diagrams does not even end there. So you see there's another approach we can have, and this is looking at the divalent ions of the first row of the D block. So once they're in their 2+ state, and this diagram, once again, we see correctly predicts all the electron configurations of the 2+ ions. But as that question on the left-hand side prompts you, you might start getting just a little bit suspicious here, because there is actually a difference in this picture compared to this picture with the first row D block atoms. Actually, another success with the Rich and Suter diagrams can be found in the F block at the bottom of the periodic table. The first row of the F block, these are the so-called lanthanide elements, sometimes called the rare earths. And again here, remarkably, the electron configurations are as observed every single time. And in fact, looking at this row of elements, it is quite interesting thinking about the the edge between the D block and the F block. So you look at lanthanum there. Lanthanum has got just one 5d electron indicated in the electron configuration. Now, in actual fact, all of these atoms have got 6s2 associated with them as well. It's just not included in the diagram. So lanthanum hasn't got any F electrons, and it forms 3+ ions characteristically in its chemistry. And so in forming a 3+ ion, it will lose a 5d electron, the two 6s electrons, and form a xenon noble gas core. And so that's why on quite a few periodic tables, lanthanum is not considered to be a lanthanide at all, because it's never got any F electrons. So particularly on older periodic tables, you find lanthanum being put in the D block. So you see a certain logic to that. It's got a D electron, partially full D subshell, and then they have the lanthanides really starting with cerium, the next one along there, and so proceeding from cerium across to lutetium. So because the 4f subshell has 7 orbitals following the sequence 1, 3, 5 from the SPD, you'd expect there to be 14 elements among the lanthanides, and actually going from cerium across to lutetium on the far right would be 14 elements. And so these are normally the lanthanides as they're, well, that's the old-fashioned way of looking at them. But actually things are a bit different now, because if you look at lutetium on the far right, it's quite interesting on this, because that's got F electrons, but it's got a completely full F subshell. It's 4f14, and it's got one 5d electron, as we see on the picture there. Also it'll have two 6s electrons, not shown. But the curious thing is that both with lutetium the atom and lutetium the ion in chemical compounds, which is 3+, Le3+, the Le3+ ion, of course, it loses the two 6s electrons, it loses the 5d electron, but again the 4f subshell is completely full. And so actually a completely full 4f subshell is actually just inert. It's no more of a F element than a completely empty one, having a completely empty subshell. And so in a way the lutetium has got a lot in common with the lanthanum. They've both got one 5d electron, and neither of them ever have a partially full 4f subshell. So in a sense there's not much in it between them in terms of which one's considered a lanthanide. But if you think about it, if you go to the third row of the D block, all the successive elements in the D block, so hafnium will be the next one, won't it? Those successive elements, they've all got 4f14. The 4f subshell is filled for those. So actually there's quite a good logical argument for saying that really lutetium is the one that belongs in the third row of the D block, because like all the other third row D block elements, it's got 4f14. So it's actually, its electron configuration looks much more like those ones. So actually these days in modern periodic tables, it's more common now to actually have the lanthanides starting with lanthanum and put lutetium at the end into the D block. So that's just an interesting curiosity that drops out of all of this. So assessing these Rich and Suter diagrams. So in a way, they just sort of seem too good to be true, don't they? Because we've got all these random and bizarre and inconsistent exceptions in the 3 rows of the D block, and yet every single one of them, 30 out of 30, are all predicted correctly by the Rich and Suter diagrams. It's even got success in the F block, it's got success with divalent ions. It just seems too good to be true, really, the Rich and Suter diagrams. And so we ask ourselves, are these the answer to all our problems? And but then we start to look at the diagrams a bit more closely. And in fact, this particularly came up when we were comparing the first row D block atoms and first row D block ions. We saw that the diagrams didn't even look the same there, despite the fact they were the same elements. And so this makes us a bit suspicious, because of course in all those 3 rows of the D block, the lines that correspond to the energy levels of the different half subshells, they were all crossing over in different places, weren't they? So actually, how do we know where the lines are supposed to cross over? And this is when we realise that actually it's all a little bit of a trick, because of course the Rich and Suter diagrams are composed deliberately, sort of engineering where the lines cross over in order that the correct configuration drops out each time. And it's quite amazing in a way that they can be constructed in a way where the correct configuration does drop out each time, because after all the lines do all look reasonably smooth. It doesn't just look completely random. But we can fix, when we put the diagrams together, we can fix where the lines cross over. And if we actually see a bit of a parallel here with the modified Slater parameters. So you may remember when we first looked at Slater parameters, we had a very small number of these parameters, these shielding parameters, which we used to model what was going on in the atom. And then when we went on to the modified Slater parameters, we basically introduced new numbers, new parameters into the model. And so by introducing new numbers, we were inevitably getting slightly closer to the observed energies. And it's a little bit like that with the Rich and Suter diagrams, because rather than just having an energy level that corresponds to each subshell, we've doubled the number of subshells effectively by looking at the spin up and spin down electrons separately. So that means effectively, we've doubled the number of parameters that we can play with when it comes to modeling all these electron configurations. And so I think there is this kind of general principle that the more parameters you throw at a problem, inevitably the better that you can model observed energies or whatever it is you're looking at there.